minus.
A three-path or a triangle and a disconnected vertex, yeah.
Yeah, so
What about this one? That's got 4 vertices. Oh, can you see what I'm writing?
yeah, wait, hang on.
Wait.
So I can write on here. So you got 4 vertices and 3 edges. There's that one too, isn't there?
Yeah, but I don't think it works.
Right, okay. But we want to say what works and what doesn't work.
Mm.
Oh, that's three edges, isn't it? Oh, yeah. We did include that. My bad. I forgot to copy down everything.
Yeah, it's fine. But the result is it doesn't work, I'm pretty sure.
Yeah, I think it doesn't work.
Lucas.
I think it's for similar reasons as that this one doesn't work. In some ways, this is a sort of just a repeat of the that one. If I remember correctly.
So then, other than that, it can be like a 3-path or a triangle and a disconnected vertex.
Yeah.
So if it's a 3-path, it can be any antiprism graph that's larger than that's not like the triangular one, the first one. So not this one. That I made a mistake copying. It's not this graph. I'll pull up another one.
Can you just scroll up a little bit so I can see that a bit better?
Yeah. Okay.
Yeah. So all right. So that's
That's wrong. That's wrong. Sorry, my bad. So something like this, I'm pretty sure would work.
Polyo PTSD.
Because
It's 1 factorizable, 2 factorable.
it's any antiprism graph that's not the one that we showed, I think.
Wait, isn't that a...
That one doesn't work.
What's a 3-path case?
That's like
10, right?
octahedron.
right.
So like I'm pretty sure the square antiprism one works.
Yeah.
Yeah, and like any larger than that also works, I'm pretty sure.
Yeah, I think this they are the infinite line one, just sort of wrapped around. They're a bit like the polygons.
Yeah. Yes, that's like the one that you showed us, yeah, the infinite kind of tessellating line. If it's a triangle and a disconnected vertex, Lucas found that you can connect 2 complete K4 graphs, and not just 2. You can connect like any number to form like
some weird.
Again, can you
some
scroll
kind
it
of
up a little bit? Scroll it up a little bit, please.
Yeah.
Yeah,
It's just I drew it really badly, but it's like 2 complete K4 graphs that are connected. So like each vertex will be connected to 2 other vertexes in the same K4 graph, which will be connected by a diagonal and connected to one other point in the other K4 graph.
Yeah. So let's see. I think this one can I draw now?
And Lucas said that we found that you could connect any number of these as long as you Yeah,
so you can think of these as pyramids. And then you can draw lines here and then put another pyramid here.
Yeah.
At each of these. And so on. And so you can get an infinite graph, but then you can also wrap them around to the full finite ones as you have. So I think if you can you see what I've drawn?
Yeah.
Yeah, we can see it.
Yeah. So I think if you take what I've drawn and then identify, I think you can probably identify these four tetrahedra to one of these.
Yeah, I think
So
that's
you probably
that's
get
what we
what
got.
you've got there, and then you can do other identifications to get other finite ones as well.
So if it has two edges, it's either like a two-path with a disconnected vertex, or it's the complete bipartite graph of 2, 2.
Mm-hmm.
Yep, so if it's a two-path with a disconnected vertex, one example that works is here. I did not format this correctly. Is this one? I think this is like the 9 circulant graph or something.
Two path with a additional vertex. So can you just scroll up a little bit, please? Oh, that's better. Right, so you've got a vertex, and
Sorry, I think I did it
two-path.
wrong. This is wrong.
I don't see a two path.
Oh, my bad. This is meant to be for the one edge case then, I think. Yeah, my bad.
Right.
This is meant for the one edge case.
Would it not be a?
Yeah, it would be for the one edge case. Sorry,
Would it not be?
it would be for the one edge case because there's only one edge here. If you take this onto the center, and they will be connected to like these two. These two are connected by one. Well,
So we're looking for every vertex to have four neighbors, aren't we?
Yeah.
Oh, okay. So this one has neighbors there and there. Okay, yes, and there's one edge. And
yeah, but it's only one edge. It's only one edge. I didn't.
Yeah, right.
Yeah.
Okay, yeah.
Do you have one then? So like a two-path with a disconnected vertex? I think you can get it. Maybe.
Two paths of one disconnected.
What you're thinking about is something like this, a two path, and then a vertex. Is that right? So
Yeah, I got confused. Yeah.
Center in, you get something like this. I suspect that's not going to work because you have, right? You have here, this is something we know doesn't work in the case of three vertices.
Yeah.
I suspect a similar argument will show that this one doesn't work.
Right, yeah. Oh yeah. See, I did the wrong picture. This one down here is meant to be this one up here. Yeah, my bad. So if it's a bipartite graph, I found this one that works. It's
okay. K22 is
it's just two lines, I think.
it's a square, isn't it?
No, it's not square, is it?
Wait, yeah, K22, like
It's not square. Oh, it is a square. My
like
bad.
this.
K22.
Oh, and this
I'm
turns
making
into square.
Yeah.
You can straighten that out to square, right?
Yeah. 2 lines. What do you get for 2?
What do you get for 2 lines?
Like triangles connected by vertices.
I found one for 2 lines, but it's not K22. My bad.
Yeah.
I'm just high.
Yeah, it's fine.
It's very unlucky.
Full screen.
Okay. This is great. Something like this works for 2 lines. My bad. Not K22.
Oh, so fine. Oh, interesting. The lots of triangles one also works.
What's lots of triangles on?
Lots of triangles. Lots of triangles.
Is it this one?
Next to this. And
it's
then
a one
these
edge,
two.
isn't it? You've got one edge there, and then two vertices not connected. So
Huh? Oh, did I just get the pictures wrong? What? I don't know, man. Oh, so this would work for the other one, right? Oh, I don't know, man.
It's just connected to one, two,
This is
four. Wait, this. Wait, that one's a triangle. Triangle and dot.
No, that one's the
Is it?
no, that one's just one line. It's for down here, so.
Okay.
Sorry, no, this one.
Yeah.
This one's meant to be for the two lines, I think.
Yeah, looks like it works.
The one you just drew on is meant for one edge. Lucas also found that. How do you annotate?
And you annotate. Oh no.
Lucas also found that
It's like
just connecting a lot of triangles works as well. As in, the vertex of each triangle is used for the vertex of another triangle, and you just keep repeating that infinitely, I think.
yeah,
I drew that figure so many times.
something like this. Sure. And then in each triangle, you put another triangle like this.
Yeah.
Yeah.
Patterns eventually.
Etc.
Yep.
So it sort of grows like a tree, but it's not a tree.
Yeah. Yeah, basically.
Yeah, that's good.
Yep. So then you have this one that we showed before for the one edge, and this one that you did.
Yeah, that one I just drew has two edges.
Yeah, well, you just drew has two edges, but for the one edge case, it's this 9 circular graph and this I think it's called like a rook graph for two I think or something. 2 4, I mean, not bad. Yeah.
I'm not sure what it's called.
Yeah, I don't know either. So it's fine.
Yeah, so that's good. So that covers all the cases then, does it?
Well, if it has no edges, whoa, what happened here? Hang on, let me just change the size of that. The sizes are really screwed up, but I think I formatted this wrong, but yeah, you have the infinite tree if there's no edges. You
Yeah.
have the grid, and I think
Yeah.
a tesseract would work, right?
Yeah. Yeah, you get a similar thing. So I think these are called hypercubes.
Yeah.
Each dimension you get a hypercube, and it has the property that the one sphere is just isolated points. So they're finite examples. Yeah. Okay. So that's all the cases then, is it?
It should be. I think it should be, yeah.
Well, that's good. I think it'd be good to
Yeah, we're good to check on them and rewrite this a bit. Yeah,
organize
sorry.
it a bit better.
Yeah.
It was looking
More
all good.
systematically.
Okay.
Yeah. I was like, that's right.
So where did you get these graphs from? Did you?
Most of them were from like Wolfram Alpha, I think.
Right.
Like this grid, and this tree was made from the
Yeah.
website that you sent us. This one I just found online, lattice graph.
Yeah.
I searched it up. I drew this one.
Yes.
That's why I look so bad. I drew this one as well. That's why I look so bad.
Interesting.
Well, that look bad.
I don't know where I got this from. Oh no, I just searched up complete graph for 5. Yeah, yeah.
Diagram.png.
Okay, well that's good. Yeah, perhaps if you organize this systematically, you can at least then start doing something for 5 vertices.
Oh,
How do you use systematic?
Maybe we so
like
we have some system about how we organize things, and do a similar thing for 5 vertices. Now I don't remember how many different graphs there are with 5 vertices, but the number grows pretty rapidly. So how many graphs are there with 4 vertices? How many cases do you have here?
Oh, I don't think we listed out all the possible graphs you could have with like these spheres. You know, I think there's like a lot more that you could do. But there's like
there's like 11 or 12.
there's
I
like
think.
11 or 12 spheres of 4 vertices.
Yeah. I think we want them all listed, even if some of them there is no vertex transfer graph, but we want to say
Yeah, I think I just missed. I forgot to put those in. Yeah.
so. You seem to be organizing them on the number of edges, so that's probably a good way to do it. Start with either a complete graph or with no edges, one end or the other, and then
Yeah, but like within a set number of edges, it gets kind of hard to.
Yeah, it does.
It gets kind of hard to organize. Like get to have a systematic way to organize them. For example,
yeah.
like the 3-edge case, I guess.
Mm-hmm. Yeah, there's starting to be more possibilities as you increase the number of vertices and number of edges. One thing you might notice is the idea of a dual graph. Are you familiar with that?
No.
So if you have a graph on some number of vertices, the dual graph is the one where you take your given graph and you draw an edge between any 2 vertices where there isn't an edge, and you delete all the edges from the original graph. Right. So it's sort of the opposite. Every time you don't have an edge, you put one in, and every time you have an edge, you take it out. So there's some symmetry in the numbers of graphs. Numbers of graphs with given number of edges. So, for example, there's just one graph with no edges, and there's one graph one complete graph.
Yeah.
There's always one graph with one edge, and there's one graph that has one edge removed. And then when you get to 2 edges, then there are 2 possibilities. Either you get a path or you get 2 distinct edges. And then the number of edges is the sorry, what was I going to say? The number of
with 2
it's half n times n minus 1 edges all up, and so you can go from 0 up to that number for your class of graphs. So when when you have 5 vertices, there could possibly be 10 vertices, 10 edges. And so the number of cases is everything from 0 to 10. And I think probably with the small cases, you could answer them, but once we start getting 3 paths and so on, or 2 paths, it gets hard to do the graphs. Five vertices, the 4 path, that's the one we don't know about, isn't it? 5 vertices and a path of length 4.
Yeah.
Yeah.
Yeah, it's 4 edges.
Yeah, so I suggest sort of cleaning up your presentation for the number of 4 vertices, and then perhaps make a start on 5. I think you'll find there's quite a few of them that you can answer, but then we can find out which are the difficult cases.
Okay.
Let me just make some comments. Can I draw? Oh, here we are. So if we have 5 vertices, we could, and say 4 edges, it could be a triangle, an edge, for example. And then, if we make our, well, it's called a cone by putting in our center and these edges. I think you can complete this one to a vertex transitive graph just by treating, if I go to another color now, treating these 2 cases separately. Right, this one we know extends. It's a tetrahedron, and we can keep building out a tetrahedron. And this one we know extends. It's a triangle, and that extends. So at every vertex, we just want a tetrahedron and a triangle. Right. So now if we come back at this vertex, say we already have a tetrahedron, so we put a triangle at each of these 3. And at this triangle, we already have a triangle at this vertex, so we put a tetrahedron here. And similarly here. And so on. So I think you can see that this one continues. So for some of the, and in fact, whenever you have 2 disjoint parts in your graph, like we have here, we have the I'm pointing at the screen. We have the edge and the triangle, two components of our graph. You can answer the question by looking at the components separately. So I think that will help to answer the question for a number of the graphs in with 5 vertices. Whenever there's more than one component, we can reduce it back to the previous cases. So it's only when there's only one component that we can't do that. And well, the 4 path is one of those cases. See what I'm saying?
Yeah. This will get rid of like most of like some of the cases that we need to do. Yeah, I get
Yeah,
it.
so it does deal with a lot of the cases for 5 vertices.
That's for dot in a triangle. Yeah, yeah, that makes sense. Because you have a dot and
Yeah.
the triangle. So you want like a what, complete
Sorry,
thing.
sorry, what's that?
I was just thinking of what you said with the and applying it to the case with the dot and the triangle.
Mhm. Okay. So you're thinking you can get some finite examples. So going back to the 5 vertices of what I drew, we could get some finite examples and maybe some mixed, sort of halfway between being finite and infinite. So that, we sort of make the tetrahedron part finite, and but the triangles we don't identify them as they grow infinitely. For example, we could do that. I think. No, maybe that doesn't work. No, what I was saying before isn't quite right, is it? No. Sorry, it was. Yeah. Yeah, with a triangle. By itself, there is only one extension. It's a complete graph, the tetrahedron. And with an edge, there's only one extension, and that's the triangle. Yeah.
Oh.
And with 5 vertices, there'll be a complete graph, a K23, won't there? And that's one that the teacher's theorem will apply to say that one we can't extend, can't be the one sphere.
Yeah, you said that you were talking to a person who
Yeah, I
had criteria.
saw him briefly, but he was in another meeting and now he might have gone. So I didn't get to talk to him as much as I thought.
All right, that's unfortunate.
Yeah. Let me just check. Yeah, I think he's gone now, sorry. All right, well, this is coming along fairly well, I think.
Thank you.
So you've got something you can continue working on here. Were there any other questions you had?
Uh, is like do people classify graphs by their spheres usually? Like, is this a standard way of classifying?
Um, Not really. This is something we're trying. This is an approach we're trying to try to build vertex transitive graphs.
I see, I see.
And so asking the question, well, given it, well, we notice that any graph can be the one sphere of some graph, some other graph, and so then that leads to the question of well, which of them can be one spheres of vertex transitive graphs? And that's what we really want to find. We want to, if we can, find new vertex transitive graphs. And so by asking this question, our ulterior motive is that maybe we can find something new, some really new graphs. Now, we're not up to the point where we might do that yet, because we're still looking at fairly small graphs, and we wouldn't expect to see anything really new there.
So this is just a method to try to generate new vertex transitive graphs.
Yeah.
So maybe like the 4-path will lead us there or something.
Sorry, the 4-path.
Maybe the 4-path will like be a new.
Yeah, if there is a vertex transitive graph there, then that would well, it's not something we recognize at the moment. We're not seeing anything that looks familiar at the moment. If there is one there, it might well be a new one. I suspect there's still not enough vertices to make it flexible in the way we want. That the group of isometries is or if we fix a vertex, that there's still infinitely many other moves we can make. That's ultimately what we're looking for, like in a tree, as opposed to an integer grid.
Right, right. Yeah, you talked about that.
I suspect that even if the 4-path does give a vertex transitive graph, I suspect it would still be a fairly rigid one. We need to go to more vertices to get something more flexible.
That makes sense, yeah.
But even finding a new vertex transitive graph, that would be a step in the right direction.
All right. Yeah, that's all I was wondering about. Yeah. Give me a call.
So you think you can write up the graphs with 4 vertices and perhaps make
Yeah, I'll fix this up, and I think we could maybe. Yeah.
Yeah, see, even identifying the ones with 5 vertices that we don't know the answer to, this is progress. We eliminate all the ones we can answer and then focus on the ones that we don't know the answer to yet.
Yep. We'll try and make progress on 5 and fix this one up.
Yeah. Now I have some meetings coming up. Well, I've got one at 4:30 this afternoon. I think I'll go home for. But tomorrow morning I have a meeting because we just heard yesterday we got some funding to organise a conference next year. And so I'm going to have a meeting with the other conference organisers because it's something we have to do before Monday.
Right.
So that's at 9 o'clock tomorrow, and then there's an examiners meeting after that, and then another meeting after that. So we have meetings all morning tomorrow.
Oh.
That sounds busy.
Yeah. I'm not keen on having all these Zoom meetings, but that's can't be helped. So we could meet in the afternoon.
Yeah, what time's good for you?
Well, perhaps I'll need to email about that because there's something else I need to check on as well.
All right then.
It might be 2 o'clock.
Yeah, that's okay.
Might be more like 4 o'clock.
That's fine.
Yeah, sure.
Yep. Okay.
Okay.
But
Yep.
I'll find out and I hope be able to email you this evening to let you know whether it's 2 o'clock or 4 o'clock.
Yep. We'll wait for Michael to forward that towards us.
Yep.
To us.
Yep.
Okay. No, empty and without a name.
All right then. I'll see you tomorrow.
All right.
Yeah. See
See
you.
ya.
Yep. See you.
Leave screen.
We set the bar room.
Wait, where's
Double click on us. Oh, the room? Hold on. Just close Zoom and it'll record there.